In section 8.3, we start looking at rational functions and their graphs that differ from the ones that we've been looking at so far. Our topics today: identify properties of rational functions and then graphing them. Okay? Our focus today will be mostly on just finding all the pieces that you need, and then tomorrow we'll look more at how we actually apply that to the graph. It says if a function has a polynomial in its denominator, its graph has a gap at each zero of that polynomial. The gap could be a one-point hole in the graph, or it could be the location of a vertical asymptote. A rational function is one where the numerator is a polynomial and the denominator is a polynomial. We will be looking at things today like this, where we have the polynomial, basic binomial, nice linear binomial, for numerators and denominators, but we will get to ones that are a little more involved than that as well. The domain of f of x is all real numbers except the values for which that denominator is 0. I've given you 3 examples here, and I do want you to make a note on your paper. This hole here isn't visible, but I'd like you to draw that in on that middle graph. Okay, the hole should be at -2, +1. So our first equation, y equals x squared divided by x squared plus 1. Okay, different shape than we've been seeing. The description down here, it says graph 1 has no value of x that makes the denominator 0. So the graph is considered continuous. In other words, you could basically graph the whole thing without picking up your pencil. There are no holes in it. There's no jumps over vertical asymptotes. It's all connected. Do you agree that there's nothing that would make the denominator 0? If you tried to figure out what would make it 0, we'd end up with x squared being a -1, which means when we square root, we'd get imaginary answers, right? There's no real number that makes that work. In the second picture, the numerator has factors x plus 3, x plus 2. Denominator has a factor of x plus 2. What is the value for x that we can't have? It can't be -2. That's why where your graph is hitting -2, we have that hole. Okay? Because it would create a 0 in the denominator. Our third picture, what can x not equal? Can't equal a +2. What do you see in the graph where x is 2? A vertical asymptote. Okay? So sometimes it will be a continuous graph. Sometimes it will be a graph that has a hole. Sometimes it will be a graph that has a vertical asymptote. That hole in example 2 is called a removable discontinuity. All right, think of it this way. If there's a hole in the ground, you can fill it with dirt, right? You can remove the hole. So a hole is a removable discontinuity. We can redefine our function and say, okay, I'm going to state that my function is this for all values except when x is -2. But when x is -2, I'm going to define it to be y being a 1. I could fill that hole. Okay? With a vertical asymptote, like in picture 3, we can't fill that. There's no way to fill a vertical line. There's too many points. Okay? So we call that a non-removable discontinuity. So holes are removable discontinuities. Vertical asymptotes are non-removable discontinuities. Now we're going to look at what makes those. How do we distinguish between a hole and a vertical asymptote? It says if a is a real number for which the denominator of a rational function is 0, then a is not in the domain. It's one of our restricted values. The graph of f of x would not be continuous at x equal a, and we would say it has a point of discontinuity. The graph that we had in that middle picture has a removable discontinuity at -2. The hole in the graph is called a removable discontinuity because we could make that function defined to be -1 there. Okay, we can fill that hole. The third picture we said there was no way to redefine it. That's your vertical asymptote. So how do we find these? To find the zeros of the numerator and denominator, we should factor them first. If you have factors in the numerator and the denominator, so something like an x minus a to a power and that same thing in the denominator, they cancel each other out, right? So think about that equation that we had in picture 2. There's an x plus 2 factor in the numerator and the denominator. If we reduce those out, we're looking at the equation y equals x plus 3. What shape would that be? Y equals x plus 3. What is it? It's a line. What's the y-intercept of that line? A 3. What's the slope of the line? A 1. Look at your picture 2. Is that a line that has a slope of 1 and a y-intercept of 3? Okay, so that x plus 2 factor was one that we could get rid of. We could remove it. Okay, in other words, the graph of this and the graph of this are identical except where x is -2. In the first equation, we'd have a hole there. In the second, we wouldn't. Okay. All right, so we're going to look at some points of discontinuity. It says, what's the domain and the points of discontinuity for each rational function? Are those points of discontinuity removable or non-removable? And what are the x and y intercepts? We're starting to look at all those details that we need in our graph so that we can actually get an accurate picture. Okay? So step 1 is to factor everything. How would we factor the denominator? X minus 1, x minus 3? Agree, disagree? Okay. Do you see any matching factors? No. All right. So we would have no holes. There's no factors that we can get rid of. But we do have some points of discontinuity. We have some values for x that have issues. Makes the denominator 0. What are those values? Okay, because we can't remove any of them, we don't have a matching factor in the numerator to cancel it out, those points of discontinuity are going to be vertical asymptotes. Non-removable. Okay? So this is a graph that would have 2 different vertical asymptotes. There's nothing we can do to get rid of them. They also asked us to find our x and y intercepts. So think about making a table of values. When you find the x-intercept, you're looking at y being 0. And when you find the y-intercept, you're looking at x being 0. Correct? Y-intercepts are probably the easiest. It's easy to just dump a 0 in for x. What do we get if we put a 0 in where all these x's are? We end up with a 3 divided by a 3. So, put a 0 in for x, we got 1 for y. Okay? To find the x-intercept, we have to put a 0 in for y. Now, I want you to think about what's going to happen here. If we put a 0 in for y, we have 0 equals x plus 3 divided by x squared minus 4x plus 3, correct? If I think of cross multiplying, picture that being a proportion, fraction equal to a fraction. When I cross multiply, what's 0 times this whole denominator? It's still 0, right? It doesn't really matter what that denominator was. When I multiply it to the 0, I'm going to still have 0. So to find the x-intercepts, we are really just saying what makes the numerator 0. Because 0 times this whole denominator is still 0. 1 times my numerator will be my numerator. Okay? So whatever makes the numerator 0 will be your x-intercepts. In this case, our x-intercept would be -3. All right? Looking at the second picture, the second example, can we factor that denominator? X squared plus 1? If it was x squared minus 1, we could factor it, correct? X squared plus 1 we can't factor. Are there any values that make that denominator 0? No. All right? So there are no points of discontinuity. That means we won't have any holes, we won't have any vertical asymptotes. It'll be a nice continuous graph. We still can find our x and y intercepts though. Okay, what makes the numerator 0? Okay, so 5 would be my x-intercept. And if I put zeros in for all the x's, I end up with -5 divided by 1. So I get a -5 for my y-intercept. Okay? The third one. Denominator doesn't need to be factored, but the numerator does. What does this turn into? X minus 4 and x plus 1. Okay? Points of discontinuity. What makes the denominator 0? A 4. Okay. Is that a factor that also appears in the numerator? So it is removable. We can reduce it out, which means this is a hole in my graph rather than a vertical asymptote. When I go to draw this picture, I'm really just graphing y equals x plus 1, but then I would have to draw the hole in. Okay? How we find the location of that hole? We know the x value has to be 4. We're going to put 4 into our simplified equation. We can't put it into the original one, right? It's not allowed in that one. It makes the denominator 0. But I can put it in the simplified version. What do I get if I put a 4 in for x? 5. So there would be a hole at the point 4, 5. All right, so I'd have a linear equation, right? I'd have a straight line, y-intercept of 1, slope of 1, with a hole. All right. What makes the top 0? Now, when you do this, use your simplified version. Because if you look at this original piece here and say a positive 4 and a negative 1 make that numerator 0, you're going to tell me there's an x-intercept at positive 4. We just said there's a hole at 4. It can't be both. Okay? So use your simplified version here. What makes that 0? Negative 1. If I put a 0 in for x, what do I get for y? All right. I'm going to pause the recording. I want you guys to talk through the how do you find vertical asymptotes and holes, and how do you find x and y intercepts. All right. It says the graph of the rational function p of x divided by q of x has a vertical asymptote at each real 0 of the denominator if they don't have any common factors where we could remove it. All right, if they do have common factors, we remove it, we get a whole. What would happen if we had, say, x plus 2 squared in the numerator and x plus 2 squared, or sorry, cubed in the denominator? What's the point of discontinuity? What's the problem value? When x is -2, okay? If you picture reducing these out, we can take the 2 from the top and reduce them with 2 from the bottom in the denominator, but we'd still have 1 left, correct? So we'd still have a vertical asymptote there. Does that make sense? It's only if you can get rid of all of them that it becomes a whole. All right, so we've got it already factored for you. What are the vertical asymptotes of that graph? What makes the denominator 0? When x is 2 or when x is 3. Can either of those factors be reduced out? Okay, so they are both vertical asymptotes. Non-removable. All right, our second one. X minus 2 divided by the quantities x minus 2 and x plus 3. What are the points of discontinuity? All right, x equals 2 and x equals -3. Okay, can we reduce either of them? Which one? The 2. So this is going to be a removable discontinuity, which means it is a whole. The -3, can we remove that? All right, so it's non-removable, which means it is a vertical asymptote. Okay? If we do remove it, this reduces to 1 over x plus 3. Okay? So what is the location of the whole? We said it happens when x is 2. What do we get if we put a 2 in there? A 5 for the denominator, so 1/5 would be the y-coordinate of that whole. Okay? All right. The third one. How do we factor x squared minus 1? X plus 1, x minus 1? All right, so we have a point of discontinuity when x equals -1. Is it removable? Okay. That means it is a whole. And the whole would happen when x is -1 and y is what? So picture reducing it out. We just have y equals x minus 1. If we put a -1 in here, we get -2. That would be the y-coordinate. Okay. A rational function can have any number of vertical asymptotes, but no more than one horizontal asymptote. That is important. We can have multiple vertical asymptotes, but we can only have one horizontal asymptote. Sometimes we will have one, sometimes we won't. Okay? So how we find horizontal asymptotes is based on the degree of the numerator and the denominator. We're going to compare them. If the numerator, and we're talking about the degrees here, okay, if the degree of the numerator is smaller than the degree of the denominator, we have one at 0, at y equals 0. Okay. If the denominator is smaller, so the numerator's degree is bigger than the denominator's degree, there isn't one. Okay, so if the top degree is small, it's at 0. If the top degree is big, we don't have one. If they match, if the two degrees match, and again, this is the degree of each, then we use the leading coefficients. So our horizontal line would have equation y equals whatever the leading coefficient of the numerator is divided by the leading coefficient of the denominator. Okay, now what does all that mean? In our first example here, what is the degree of the numerator? What's the power of x? 1. Denominator also is 1? So they have matching degrees. Okay? The degree of the numerator equals the degree of the denominator. We then go to our leading coefficients. So we would have a horizontal asymptote at y equals, and for us the numerator is 2 and the denominator's leading coefficient is 1. So we just get y equals 2. Okay? We are using those leading coefficients. So the 2 here and the 1 there. Our second example, looking at the degrees. The top degree is 1, the bottom degree is 2. You're looking for degree, so it's the highest power of x in the numerator and denominator. So top degree is 1, bottom degree is 2. When the top is smaller, what happens? So the degree of the numerator is smaller than the degree of the denominator. We have one at 0. Okay, the x-axis. All right, third example. What's the top degree? All right, so top degree is 2, bottom degree is 1. That means the degree of the numerator is bigger. What happens? All right, so you guys know how to find x and y intercepts. You know how to find vertical asymptotes and holes. And you know how to find horizontal asymptotes. Those are the key features that we will be using to figure out our graphs. Okay? All right, talk at your tables. I just want you to go through A, B, and C here and decide, is there a horizontal asymptote? And if so, what is it? All right, what do you notice in the first one? For the degrees are the same? They're both 1s. So we use what? The leading coefficients, yep. So y equals -2 divided by 1, or just -2. Okay. Second one, top degree is 1, bottom is 2. So the top is smaller. Where's the asymptote? Okay. And in the third one, top degree is 2, bottom is 1. If the top's bigger, all right. So you guys are going to go ahead and do day 1's assignment, 13 to 27 odd, 36 to 38, 50 to 52, and 55 to 60.